Alright, so this video is about an application of moments of force. Alright, the application is called the rule of moments. Now we're going to get into what that means, well, now, okay? So basically we're going to use a balanced beam. Alright, this is a beam and it's balanced at the center there. It's got a pivot point. Alright, and we're going to use that to calculate an unknown force. Okay, so let's go. So here's an example of the setup that we're talking about for this. Alright, so we've got a beam here. Right there's a beam, and then we have some string, alright, represented by those lines, and then we've got two rocks here. Okay, this rock is bigger than that rock, and we have set them on the beam so that they balance. Alright, one thing you might notice, the bigger rock is closer to the pivot than the smaller rock. That's because the bigger rock has a larger weight, a larger force of gravity acting on it, and the smaller rock has a smaller force. So in order to balance the beam, the smaller rock has to be further away from the pivot point than the bigger rock, or the heavier rock, right? So the reason for that is that you get a larger moment, or a larger turning effect, the further you are away from the pivot. Clearly, right? Because moment is equal to force times distance, as you recall from the previous video. So the force times the distance. If we have a smaller force and we want the moment to equal the moment caused by this guy to equal the moment caused by this guy, then we need a larger distance for a smaller force. All right, anyway, that gives you a larger moment. All right, and larger force, you need a smaller distance so that you can equal so that the moment caused by this guy is equal to the moment caused by this guy, but opposite. All right, so this is an application of equilibrium conditions. All right, let's get into the nitty-gritty details of this here, okay? So we have several things, distance 1, distance 2. Distance 1 would be the measurement from the pivot point to the line of action of this force. So in other words, the point where the rope is here, attached to the beam, and then distance 2 is the distance from the pivot point to the other rope that's supporting this rock. All right, so the moments, according to equilibrium, right, we say this beam is in equilibrium, it's not moving. So according to equilibrium conditions, the moments have to cancel out. All right, and remember, here's the equation again, moment is equal to force times distance. So force 2 times distance 2 has to equal force 1 times distance 1. All right, okay. So let's work with that a little bit more detail. All right, so here we have that picture reproduced one more time, and the conclusion basically of what we were just saying, we said the force 1 times distance 1 causes a anti-clockwise moment, and then force 2 times distance 2 causes a clockwise moment around this pivot. Those have to be equal to each other. All right, so this right here, bam, bottom line, this is the rule of moments right here, also sometimes called the law of moments. All right, if a beam is in equilibrium and it's experiencing more than one force, all right, well, yeah, and it's experiencing a couple of forces, then the clockwise moment caused by, this force would cause a clockwise moment, all right, has to equal the counterclockwise moment or the anti-clockwise moment, and that's what this one would cause. All right, so this one is going to cause the beam to rotate this direction if it were by itself. This one causes the beam to rotate this direction, but since they're both happening at the same time and the beam is in equilibrium, then this one is equal to that one, and we get this is the rule of moments. All right, this equation right here summarizes the rule of moments for this particular situation. All right, so let's apply this to some concrete examples. First, all right, so here we have a problem taken from the multiple choice IGCSE physics exam. Okay, so right here we have several diagrams that show a uniform rod. That means it's the same all along its length, okay? And its midpoint is on a pivot. That means the rod without any forces should balance on that pivot, okay? Now we add forces. So 2 equal forces then are applied to the rod. And then we've got 4 different situations, A, B, C, and D, of how those forces might be applied to the rod. All right, and then the question is, which diagram would be in equilibrium? All right, so according to our rule of moments, if the rod is going to be in equilibrium, then the total clockwise moments have to equal the total counterclockwise moments, right? Well, let's check pivot A, or situation A. This force is going to cause a moment that direction, which is anti-clockwise. This force will cause a moment that direction, which is anti-clockwise. So there is no clockwise moment at all, which means this rod will just spin. So that one is not in equilibrium. Nope, not that one. All right, so moving along, let's check this one out. This force is right at the pivot, right? So it's not going to cause a moment at all. It would just tend to try to lift up the rod. And then this force is going to cause a moment this direction around the pivot, so that's clockwise. There's no counterclockwise or anti-clockwise moment, so bam, that one's not going to be in equilibrium either. All right, next, we've got letter C. All right, so we've got a force here that's equal to the force there. All right, they're applied at the ends of the rod, so you can tell that's going to be equal distances from the pivot, which is at the midpoint. All right, the force here is going to cause an anti-clockwise moment. Force here is going to cause a clockwise moment. They're equal forces, they're equal distance from the pivot. So, bam! That's the guy. That's going to be in equilibrium because it matches the rule of moments. All right, and then this one, you can see again, they're both going to cause, since this one's going up on that side, it causes a clockwise rotation. And then this one would cause also a clockwise rotation. So this guy doesn't have any balancing. It doesn't have any anti-clockwise moments. So it's just going to turn. Cool. Now a little bit more detail here. So we've got it tells us we've got a circular metal disc. It's got a pivot point at the center. And then it's got several holes where you can hang masses from it. It says that those holes are 4 centimeters from the pivot, 8 centimeters from the pivot, and then 12 centimeters from the pivot. So there's 4 centimeters between each of those holes. Right. Now, they want us to balance this by hanging 2 masses in the holes. All right, but we have to choose 2 different masses. So essentially, the easiest way to do this, all right, they give us options. These are the masses that we have access to, 1 of each. All right, so we have to use 2 different masses, and we want this thing to balance at the end. So we can hang these from the holes, all right? So basically what we need to do is we need to pick 2 masses. The easiest way is to pick 2 masses that are double of each other, right? That one is twice as big as the other. So if I zoom in here, I could pick the 100 gram and 200 gram, or I could do 200 and 400. You know, it's really up to you. There's several different options of what you could do. I'm going to do just to be simple, I'm going to pick these 2, the 100 and the 200. Okay, so the 100, now if you think this through, 100 grams is half the mass of a 200 gram, which means it's going to have half the weight. All right, so I'm going to have to put it twice as far from the center. So I'm going to hang that one from the 8 centimeter hole right there. Now let's redo that. Hang on. Redo that. All right, and we're going to make this the 100. I'm just going to say 100. All right, 100 mass, 100 gram mass. And then we need to hang the 200 gram mass from the 4 centimeter hole. All right, it has to be half the distance of the 100 gram mass. So 200 goes there. Bam! All right, so that's how we would do that. That's one example anyway. All right, let's go ahead and really quick, we'll do another example. Let's say we wanted to use the 100 gram mass and the 300 gram mass. Well, we'd have to, the 300 gram mass is heavier, so that one's going to have to go from this hole. All right, so let's zoom in here so we can see a little better what we're doing. All right, so 300 we'll put it there at that hole. And then the 100 gram mass is going to have to go 3 times as far away, so that would be our third hole over here. I'll say that's the 100 gram mass. Alright, so then 100 times 12 is going to equal 300 times 4. Alright, we could check ourselves by doing that math, but I'm not going to do it because this video is already kind of long. Alright, cool. Thanks.